Hi again, everybody. Today we're going to finish off talking about discrete random variables. We'll look at a couple more that we haven't seen yet, that are both of them which are pretty famous, geometric distribution and the Poisson distribution. Those will come up a lot in later classes. And then we're going to move on to continuous random variables, where you'll see straight away that it's a little bit more delicate. How do you kind of describe these guys? The probability mass function doesn't really work anymore, and we have to invent a new thing called the probability density function. So we'll talk about that for a bit. And then we'll just introduce a really quick one, the very easiest one you can imagine, which we'll call the uniform distribution. It's going to be our first continuous random variable distribution that we'll see. All right, let's dig in. So our next guy up is the geometric distribution. It's named after the geometric series, as far as I know. And the geometric distribution, it's sort of similar in a way to the ones we've seen so far. So the distributions we've seen so far are very understandable. You could, once you kind of know what they are, if you thought about it slowly enough, you could write down what the distributions should be. Or at least that's how the lectures were intended to have gone, that if you thought through them as I was writing them or as you were writing them, they should make sense. The geometric distribution is similar. So this one is like the binomial distribution in a way. So it's like binomial in the sense that it's based on a series of Bernoulli trials. So also used for a series of Bernoulli trials. So these three distributions, Bernoulli, binomial, and geometric, they're all very closely related. So in the case of the binomial distribution, in that case, the random variable x was usually the symbol x was the number of successes. Let me erase that. Number of successes after n trials. And let's just say these Bernoulli trials that we're dealing with, they have a parameter, a probability of success, p. So there's some parameter for our Bernoulli trials, that's the probability of success. The binomial distribution has that parameter. It inherits it from the Bernoulli distribution, but it also has another parameter, which is the number of trials. And the random variable you try to describe is how many successes do you get after n trials. So this time, the new one, this time, we deal with the geometric distribution. And it's a bit different. So here, x is going to be the number of trials needed, or the number of trials before your first success. And it turns out this has a simpler distribution because if you think about it, in the case of the binomial distribution, you're trying to describe the probability of having some number of successes after a fixed number of trials. Well, there's lots of different orders in which those successes could come, right? So if you're flipping a coin and counting how many headses and tailses you got, right? The first one could be a heads, then maybe the next one isn't, and then the next one is a heads, and that's a case of two heads, right? But another version of that is the first two tosses are heads. And so in both of those cases, you got two heads. There's different arrangements, right? But for the geometric distribution, where you're looking at the number of trials before your first success, you're much more limited because all the trials before your first success are failures. So it's fail, 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 and then a success. right? And so there's only one arrangement that you can actually have if you know how many trials have been taken. So so let's write down the definition, the more formal definition. That was just kind of a little rambling definition. So here's our more formal definition. And so this, we're going to describe the definition of the geometric distribution. So we'll say if some discrete random variable has a geometric distribution, so that's what we're talking about here, the geometric distribution, with a probability of success parameter p, which it inherited from a Bernoulli distribution, and then that's in the range 0 to 1, in the interval 0 to 1. Right, then the following things are true. So this is just the defining properties. So first, this one's sort of just, our definition is going to include this way of writing it. So we say x tilde, meaning it follows the such and so distribution, or it has the such and so distribution. You can read that in different ways. Or, so we'll say x is distributed with the distribution. There's lots of different ways. So we'll say, we write this as GEOM P. All right, so GEOM stands for geometric, and P is the only parameter in the distribution. So that's one property. It's really not, I don't know if that really belongs in the definition, but that's how we're going to write it. X can take on integer values. You can take values 1, 2, 3, and so on. It can't take 0. Because it can't be the case that it takes 0 tries before you have a success. You have to at least have one try. And it has the following PMF. So X has probability mass function. And if you think this through, you probably could write it out. But I'm just gonna write it out here. You can think it through as I'm writing it. So we say f of x, that's the PMF. I think I might be writing on a line break right here. So my apologies. I usually try to avoid these things where this line goes like that, because if you then print out the notes, it chops it, but we'll see how it goes. So the PMF looks like this. So we'll define in this piecewise case, of course. So the way we've been doing is a little bit pedantic, I think. But so if x takes on values of 1, 2, and 3, and so on, then it has some interesting formula. Otherwise, it's 0. In other words, the random variable x can only have the values that I'm about to show, 1, 2, 3, and so on. And so for that, what is the probability that you have this many, how do I say it? This is that after x, you have had your first success, right? So if you've done that, how many fails have you had to have, right? And how many successes have you had to have? So, well, you've only had one success, so that's p. So one success times the number, or the fail probability, so 1 minus p, to the power of however many fails you had. So that's x minus 1. Now, in the case of the binomial distribution, we saw that same sort of a term. It wasn't just 1 and x minus 1. It was like n and x minus n or something like that. But then there was some coefficient in front for the number of different combinations or different orderings of your results. And here there's only one order, that they're all fails, and then you have a success. That's kind of the whole nature of the thing. And much like the other distributions, this one has lots of applications, but this class isn't really so much about telling you what all those applications are. It's rather kind of introducing them, the sort of main players. All right, so let's check its properties. Sort of, right? So check its properties. Make sure this works. This is just a good habit. Oops. If you haven't noticed already, I have very funny spelling habits when giving lectures. I sometimes, yeah, you might have just seen it. All right, so let's check its properties. So what properties does it have to have? It has to have, first of all, it has to have the property that f is in between, so f of x is in between 0 and 1 for all different values of x, and that's true, again, by inspection. Be a little careful with that. You don't want to be saying everything is by inspection and then you catch out that you inspected wrong. But the other condition, right, I think I called that property 1 last time, so let's put those numbers on there. So that was property 1. And then property 2, the so-called honesty condition, right? This one says that you got to do a sum from over all possible x's. So all the x's that are smaller than 1, those are 0. So we go sum from x equals 1 to infinity of f of x. So that should be 1 by the honesty condition. So what does this sum look like? So it's the sum of x equals 1 to infinity of p times 1 minus p to the x minus 1. Or you can rewrite this to pull out the p. Like that. Oh, sorry, I wanted to do one other thing before I did that. I wanted to rename the index. Sorry about that, guys. So I'm going to make a new index, and I'm going to call it u, and that's just going to be x minus 1. Right, and so u then goes from x started at 1, so u goes from x minus 1, so that's 0 to infinity, and then this is just u. And so then you see the geometric series is presented in its sort of traditional format. And I don't know if you remember this or not, I think we used it in the last time, but I may as well, since this one is called the geometric distribution, we may as well write it out. So the geometric series, so I'll just say recall. I'm not going to prove it, but you should be able to. So recall the so-called geometric series. And then, so this is the sum x equals 0 to n minus 1. A times r to the x. And this thing has value a times 1 minus r to the n over 1 minus r. You should have used that a lot by now. And this is the formula for, of course, when r is not equal to 1. Otherwise, this formula is no longer valid. I get that there. That's r is not equal to 1. All right, and so if we apply that here, what do we have? So first of all, we have n is going to go to infinity. We have a, well, that's p, I guess. Oh, well, it depends how you want to write this. You could put the p back in there. Let's just call it a is equal to 1. And then what else do we have? We have r. Well, that's 1 minus p. And notice that r is then bracketed by 0 and 1, right? Because p has limiting values of 0 and 1. Yeah, and so those are our different parameter values for the geometric series. And so if you put those in, what do you get? Well, you get the sum x equals 1 to infinity of f of x, the thing that we were looking at. This becomes p. And then in the numerator, you have 1 minus r to the n, but r is less than 1 and bigger than 0, and n goes to infinity, so that numerator is just going to be 1. And then in the denominator, you've got 1 minus r, and r was 1 minus p, so this becomes minus 1 plus p, right? And so this is 1. And so the honesty condition checks. I think in your notes it might have said something like, we'll check these conditions in your tutorial sheet, but we didn't. I think I took it off the tutorial sheet this year. I thought I would just show it in the class. All right, and now there's this interesting, so this distribution has a sort of an interesting property that gets a famous name. So I'm just going to say note. If you have a random variable x that has a geometric distribution with parameter p, there's this kind of cool property. So this thing has a property, and I'll just write it down here. The main thing about this property, I think, right now is just to see what it is, not so much to prove it. So it's the probability that x is bigger than x plus u, given that x is greater than u. That turns out just to be equal to the probability that x is greater than little x. So that's an interesting property. The thing on the left is saying, what's the probability that I have to go x plus u trials before I get my first success, or bigger, if I know that I've already done u trials and not had a success? And it turns out that the fact that you've gone the u trials is kind of not important. And the answer is that probability is actually just the probability that x is bigger than little x. And so that's kind of an interesting property. It has a name. It's called memoryless, or without memory. Memoryless. I've seen this come up a few different cases in problems that were interesting to me, and the name made good sense there. You might see it as well. I think you'll see it a lot if you take the Markov chains and processes class, which is offered, I think, in the first semester of next year, I think. But anyway, so this is called the memoryless property, and there's a proof for it. We used to have a problem that we would give you guys in tutorial 3 that has a proof, and you'll see it says that in the notes. But I took that problem kind of out, and so I'll sort of sketch for you the proof. Parts of the proof are in the tutorial. So proof sketch. So proof sketch, not really a proof. I hope that I can convince real mathematicians, remember I have a physics background, to accept this terminology, proof sketch. If you get points taken off on an exam, say, oh no, that was proof sketch. Proof sketch. Sorry, I didn't realize we were doing real proofs today. Yeah, so proof sketch, here we go. So the way you do this proof is kind of like this. So the first thing you do is you find the probability that x is greater than 1, right? So you work that out. It's relatively straightforward. Then you find the probability that x is greater than 2, right? That's also relatively straightforward. And then from that, you surmise, you make a wild guess, or if you like, prove it, the probability that x is greater than n, where n is any number. So you make that progression right there, so that you end up with a statement about the probability that x is greater than n. So I'm going to kind of underline this guy because it's going to be important, and we'll use it at the later part of the proof sketch. All right, and so then the next thing you do is you kind of construct the probability that you're interested in the left-hand side here, this guy here, right? You're going to put that on the left-hand side, and then on the right-hand side, you'll sort of break it up using Bayes' theorem, or like the definition of conditional probabilities. So we've got the probability that x is greater than little x plus u. So this is the thing we're interested in, given that x is greater than u. And then on the right-hand side, we have this ratio. And in the numerator, you've got the joint probability that x is greater than little x plus u, and x is greater than little u. All right, so that's the numerator. And in the denominator, we just have the probability that x is greater than u. Hope I wrote that down correctly there. That's another danger with proof sketches. Since you don't show all the steps, you might not catch all your mistakes. But so now if you think about that numerator, if little x is always like 1 or bigger, that probability in the top of that fraction, it's really just the probability of the first piece. Because if x is bigger than x plus u, it is definitely bigger than u. So this numerator is simpler, so it's really the probability that x is greater than x plus u. Sorry, that's meant to be little x there. My big and little x's often get confused. And so that's what the numerator now looks like, and the denominator still looks the same. Right? And now you take your rule here and you use it twice. You use it once for the numerator and once for the denominator. And then by the power of proof sketch vested in me, you get the answer. Like that. All right, proof sketch complete. Maybe, I don't know if we get a little square for this. Little square, maybe something like that to remind you. I don't know, put some kind of fun symbol there to remind yourself that this is somewhat bullshit. But it's pretty close. Anyway, so if you follow these steps, I think in the tutorial you'll do this and you'll do this, and then I think we skipped off the part where you would do this and figure out what that is. But you should be able to do that. That's pretty fun. Yeah. All right. So that's the end of the geometric distribution. Now we get to our next distribution is called. Well, I'll name it in a second. Next distribution is different than the others in that you're not going to be able to you're not going to really fully own it in the way that you have the others, because it's not so obvious why it is what it says it is. But that's okay. I mean, we can certainly check that it's a valid probability mass function and that all is well. Whether or not it actually kind of has application and stuff is going to be a little more opaque, I think, this time. But that's kind of the way it goes when you're just seeing the greatest highlights of something, which is what we're doing here. So this one is called the Poisson Distribution, named after a person, not a fish. So the Poisson Distribution. And this one, it has a lot of applications that I can kind of describe to you a little bit, but it's a little unfair because telling you about these applications is not going to make it obvious to you that the distribution has the form that it does. But nevertheless, I'll tell you, so I'll say it has applications related to counting occurrences of something over a time interval. Or to counting occurrences over a time interval or a space interval, like an area or a volume or something like that. With a rate parameter, so we'll say at rate. So this is just the name of the parameter. And the parameter is usually written as lambda, and it's positive. It's a real number that's greater than 0. So some examples of this are some mundane examples, if you ask me, are like the suggestion is given in the notes, like how many phone calls came into like a help center over some particular amount of time. Or it's kind of, I think I encountered this in physics the first time with a particle detector experiment, and the Poisson distribution was used to describe the number of particle detections over some period of time, or particle interactions. It has lots of applications, but again, we're just sort of claiming this. You're not really going to you're not going to look at this and say like, aha, I knew that had applications to occurrences of things over an interval of space or time. So I'm afraid that you're going to be kind of left out there. But hopefully you'll get to see that again. And then you'll come to be a firm believer. But okay, so what is this guy? So we say if a discrete random variable has a Poisson distribution, with rate parameter lambda. I don't know if everybody calls it the rate parameter, so maybe I shouldn't be calling it that, but I'll call it that. You could just call it parameter, but with rate parameter lambda greater than 0, then the following things are true. Again, the first one is just going to be our notational thing, so we write x tilde. We are going to write PO for the first two letters of Poisson. I think I've seen this written elsewhere as POIS. It's very frustrating sometimes when you encounter something like this and you don't know what the person is talking about. It isn't actually super universal what people call these things. So don't be afraid if you're in some situation where you can't tell. Go ahead and ask. But we're going to be expecting you to know these symbols, the ones that we put in our definitions here. Then x can take on, it can take values. This part you should be kind of able to understand if you believe me that what it's used for counting how many occurrences happened over some interval of time. So it's going to be 0, 1, 2, and so on, up to any integer, any value there. And it has the following PMF. And I'll just write it down. So it looks like this. So it's f of x again. And again, it's going to be piecewise defined. So it's going to be something interesting for x equaling 0, 1, 2, and so on. And then something that is just going to be 0 otherwise. A lot of people won't write this so carefully like this. They'll just write the interesting part and then say, and just leave it up to you to realize that it's 0 elsewhere. But we go that extra mile here in this class. So this is lambda to the x times e to the minus lambda. That's e as in exponential e. Oh man, I really made that a hard looking, like that, over x factorial. Now, so again, I don't think you're really in a position to look at that and say, like, absolutely, that is absolutely the probability that some number of occurrences happened in some time interval, if they were occurring at a rate lambda. I think you can't really see that. I can't see it. And so in this one, we're not going to check its properties. So check its properties in your next examples class. So you'll get a sheet with problems to work on for your next examples class, and it's in there. All right, we'll do a little kind of application, or it's not really an application, but we'll just try this, take this thing for a little test drive. So we'll do a little example problem using the Poisson distribution. Just see if we can do anything with it. So let's suppose you have two random variables that both have Poisson distributions, but they're different distributions. And we'll suppose that they are independent random variables. So let's say let x be Poisson distributed with parameter m, and y be Poisson distributed with parameter n. Let's let these be independent. All right, so those are independent discrete random variables. And I want to find out, so the big challenge of this example is I want to find the probability that x plus y, oops, oh no, is equal to 1. right? So that's what we want to do. We want to find that probability. Now, this is a sort of a straightforward thing. So probability that x plus y is equal to 1, right? There's only two ways that this can happen. So think about if these things, if x and y are like counting instances, maybe I don't know, let's see. X is maybe counting some particular particle hitting a collider, hitting a detector, and y is a different kind of particle hitting a detector. And so what is the probability that the sum of the two is actually 1? So you got one event from one of those particles hitting the detector. So x plus y is equal to 1, so that's what we want. So this can happen only in two different ways, right? You either get the probability that x is equal to 0 and y is equal to 1, so that's one way. Or you get the probability that x is equal to 1 and y is equal to 0, right? And if these things are independent, then this is the probability that x is equal to 0 times the probability that y is equal to 1 plus, and then you get the idea, x is equal to 1 and then y is equal to 0. I hope you get the idea at least. And now I'm going to sort of steal this thing because I'm going to use it a couple of times and I always mix up what goes where. I guess I'll just duplicate. I'll just bring it down here for reference while I write this stuff out. Man, I wish I could do that on the blackboard when I'm way on the other side of the room. Alright, so what's the probability that x is equal to 0? So remember, x has parameter m. And so we've got m to the 0, e to the minus 0. Oops, no, e to the minus m. Sorry about that. Divided by 0 factorial, which is 1. Times the probability that y is equal to 1, and so that's going to be n to the 1, e to the minus n, over 1 factorial, which is also 1, plus, and then over here, we just have m and n are swapped, the second term. And so what is that? So that's n times e to the minus m plus n plus, and then we just write the same thing but swap them. So that's m e to the minus, and then this is actually the same, right? So we get m plus n e to the minus m plus n. Yeah? All right. Okay, so that was just our little test draft. And you could put it, I think the example in the notes actually asks you for different numbers there. But I thought it would be fun to just do it symbolically. All right, so now we get on to our next kind of sort of significant topic, which is continuous random variables. And these I'm going to use the same kind of acronym, CRV. I guess maybe you put a little s under there for make it plural. And so continuous random variables is a somewhat biggish topic. Oh my goodness, what did I do? Let's see if I can make a square. Sometimes it doesn't know what I'm trying to do, sometimes it does. There we go. So continuous random variables. And this is going to be kind of our next major topic. And we're going to proceed in a similar way. So we'll first just define what a continuous random variable is, and then we'll introduce some examples and talk about them. So I'll just go straight ahead with the definition. The definition is not very difficult to understand if we've already seen discrete random variables and just random variables altogether. So a continuous random variable, CRV, which I don't know if it's true in the UK, but in the United States there's a car made by Honda called the Honda CRV. I wonder if they know that maybe they're mathematicians. Yeah. A continuous random variable is a random variable that can take on a continuous range of numbers, values, can take on any value within a given range. And so we'll write, and the range can be finite or infinite. There's no reason to write that, but it's just true. The random variable, it lies in that interval with some probability. Or lies in any other interval. So I'll call this interval A and B, like that, with some probability. I should say I've kind of required, I've sort of buried in here that A and B are both real, and A is the smaller one. Yeah. Okay, and so this is the definition of a continuous random variable. So I guess I'll highlight that's what this thing is. Yeah. And so we'll try this out. What's really going to be interesting, this notion is probably somewhat straightforward to what a continuous random variable is, but what's really going to be interesting is the generalization of the probability mass function. Because if you think about it, so we'll just pause here and think for a second. Imagine that you had a continuous variable, like say temperature. And you ask, what's the probability that the temperature is such and so? And you put down some real number, right? Like 35.932, whatever. And you keep on going forever, right? What's the probability that the temperature is exactly that number? It's 0, right? Because it's never going to be exactly that number, or at least almost approximately never. So there's this interesting kind of conundrum here. So how are we going to make up a probability mass function for this? But yet somehow you still ought to be able to say things like, it's more probable that the temperature is 20 degrees Celsius than it is 8 million degrees Celsius when I walk outside my door. So you ought to be able to do that, but the probability of either of those two numbers, being the temperature, is 0. And so we need that's the part that's interesting about continuous random variables. So let's make a little definition here. What we're really going to define here is the analog of the probability mass function. So the name is going to show up at the very end. It's called probability density function. But it's going to show up at the end of this definition. So we'll say for a continuous random variable y, we could have used x. I don't know why we switched to y. For a CRV y, if, and then I'm just going to repeat all that stuff. A, B isn't real. A is smaller than B. I guess that's I've got that in the definition, so I guess I don't have to do that. I think in the notes it's not in the definition. Then the probability that y is in between A and B, that's equal to the following. It's integral from A to B f of y dy, where f is our analog of the probability mass function. And so I'm going to write in the definition, I'm going to put its properties. So where, I'll put 1, f of y is greater than or equal to 0 always, and 2, the integral from minus infinity to infinity of f of y dy, that's 1. Right? So these again have the names, 2 has again the name normalization or honesty condition. Right? So if these things are true, then f of y is the probability density function. I should use a capital, I guess. That's the definition of probability density function. It's also called PDF, which has nothing to do with the name of the file format, which means portable document format. So the probability density, which confused me immensely when I was an undergraduate. I was like, who's naming these file formats? Yeah, so probability density function, the PDF for Y. All right, and so we'll just point out a couple of key features, since the two conditions are I buried them in the definition here. So notice some interesting things. One I've already pointed out. If Y is a CRV and its PDF is, or yeah, I don't even have to say anything about its PDF. Notice that probability of Y equaling little y is always 0, right? Because if you think about what's happening here, right, if this thing is some sort of an integral, right? So let's say f, some sort of shape like that. I don't know why we always use that shape as an example. You could use other shapes. Then if this interval a to b, like this is a, this is b, then this, oops, well, I'm making a big mess there. Then this is a probability of the area under the curve. This thing, the probability density, is not a probability, right? So it's only areas. And so you can see, like, if you ask what is the probability of being at one particular value, that means the area underneath one particular value, and it's always going to be 0. But yet somehow you can still look at this and see that it's more likely that you'll have the value b than the value a. In fact, you run into this thing called likelihood function, which is a conditional probability density function. You'll find that at some point in your lives. All right. And so now we can try, there's one other point that I just made, that f of y is not a probability. So you have to be careful with that. Okay. And also it's worth pointing out, look, this is kind of interesting here. This thing, whoa. This thing here, that sort of positivity type condition is different. It now just says f has to be bigger than 0, but it could be 1,000 or 1,000,000. But as long as it doesn't stay that high for very long, you'll be okay. And that's enforced by this business here. All right, so we'll try a little example similar to the one we did before. Once we've defined a continuous random variable and its probability such and so function, so density function in this case, we'll ask yourselves which is a valid PDF. Let's show some examples here. A. So this one, for some reason, in the notes they start with this, and it's a really bizarre one. F of y is equal to 1 over n, where y can have values 1, 2, ... up to n. That's really similar to one we've seen before, except that this limit here is different. Or I think that's different. That's not different, but it started from 0 before, and it starts from 1 here. So there's n of these guys, not n plus 1. And that means, well, yeah, I'll get back to this in a minute. Okay, next candidate. Just a spoiler alert: A is not going to work. It's got a lot of problems. But anyway, so next candidate. F of y is equal to e to the minus y for y greater than or equal to 0. C. F of y is equal to y minus 1. And then what do we have here? So 0 less than or equal to y. So y is in this range, 0 to 1. And then D, f of y is y to the minus 3. And we'll say y is greater than or equal to 1. And then for all these things, we'll say 0 otherwise. That's kind of missing in the notes. So all these potential PDFs are 0 for any y that is not specified on the right-hand side there. All right, so what are the conditions, right? We got this positivity condition, and now it really is just positivity. In fact, maybe we should even name it. Do we have room up there to fit that? Let's just leave that to you. Number 1 is positivity, and number 2 is honesty. Oh, I should write that. So it sounds so lovely. Positivity. Got to be positive and honest. And this is honesty. What a lovely subject. It's just nothing but positive and honest. Except for all the things that don't work. All right. So are we positive and honest? We just have to ask that of each of these F's and then throw them out if they're not. All right. So first of all, check the positivity. That's the easiest one to check in this case. And I'll just look at these. So this is always positive because the right-hand side is a positive number always. There's not much to say here. This is always positive. E to the anything is always positive. This guy, not so much. It could be negative, right? And let's see, is it ever? Yeah. If you just put in y equals 0, you get this guy to be minus 1. So that guy's out, right? So positivity. He's not positive. We only accept positive people here. And then this last one, is this guy always positive? Y to the minus 3? Well, it wouldn't have to be, except that y is greater than or equal to 1. So, yeah, so positivity ruled out one of these guys. Now let's check honesty. And so for each of these, in principle, there's an integral. Now I'm going to leave A for last because it's completely absurd. But so let's just look at D. Start from the bottom. So I want to look at the integral from minus infinity to infinity of y to the minus 3. Oh no, it's not minus infinity to infinity. Sorry about that, everybody. Right, y is only allowed to be greater than or equal to 1. And so this goes from 1 to infinity. dy, right? And so what is this? Oh, my powers of integration. So this is going to be 1. It's going to be minus 1/2 y to the minus 2. Yeah. And then infinity and 1. And so what do we got here? When you put, so we got minus 1/2. I'll just take that out. Y to the minus 2. When y is infinity, that's 0. And then minus 1. And so this is a half. So it's out. It didn't satisfy. It was positive, but it just wasn't honest. Out. And now let's check B. All right, so what's that? E to the minus y. E to the minus y dy. I gotta look at its limits here. It goes greater than or equal to 0. Like that. Here we're going to be in business. It's because this guy is minus e to the minus y infinity 0. And so that's minus 0 and then minus 1. Famously called 1. Okay, so B is in business. Now, A is just so wrong. Let's just see why it's wrong, all right? So let's just draw it, all right? So here, the horizontal axis is going to be y. And then this guy's going to be f of y. And let's just look at, so this is, I'm checking out A here. And let's just say we take the case n is equal to 5, right? It could be anything. I may as well pick 5. Why not? It doesn't have to work. Or if it doesn't work for n equals 5, it's over. So, okay, so then you go over here and say, what values can y take on? Okay, now 1, 2, 3, 4, 5. That's all it can take. So, okay, 1, 2, 3, 4, 5. And for every one of those,
the probability density function is a fifth, like this. And everywhere else, it's 0. Right? So it's 0 here, 0 all in here, in here, in here, in here. 0 all this. So this is like, it just jumps up there to a fifth. Like that. And so look, come on, what are you going to integrate that? What is that? The integral, the area under all of those dots is 0. So this is just so out, right? So it's not honest. So dishonest. Yeah, so that's out. Dishonest. Okay. Let's see if we can't see an example. We're just very quickly going to look at one little example. It's said in the notes that this is the simplest example of a probability density function, but in a way it's not. It's called the uniform distribution. In a way, it's one of the more weird ones. Right, so the uniform distribution, I should have been doing this in red. I can change it. Change you. Boom. I'm never going to get tired of this notepad. So the uniform distribution, this one comes up all the time. You've used it a million times. You've used it whenever you've said, pick a random number. Between A and B. Maybe you didn't always say it that way, but like when you're a kid, pick a number between 1 and 10. Incidentally, when you say random in this context, it's implied usually in everyday language that you're talking about a uniform distribution. In the mathematics, in our world, random doesn't mean that. It just means described probabilistically. Some people think that's another way to say that is to say it's stochastic or something. I don't know that really helps. But random just means described probabilistically. And so in this context, though, in this sort of everyday language context here, when you say this to somebody, what you're actually meaning is pick a random variable, assign a continuous random variable with a uniform distribution, a number, or something like that. So you're implying a uniform distribution when you do this in everyday life. So let's just look at the definition here. All right, so we say that if a continuous random variable, if a CRV y has a uniform distribution, over the interval A to B, where again, that same old song, A and B are both real. I think that's a clumsy way to write that, but I'm going with it. And A is less than B, right? Then the following things are true. So this is what we're defining uniform distribution here. Then we say y tilde, just the letter u, and then there's two parameters, A and B. Some people write that as UNIF. But this is the notation that we're going to stick with and that we will want you to use. And also, y is it's restricted somewhere between A and B. Right? And lastly, most importantly, and y has PDF, probability density function. I start mixing those up all the time now. That looks like this. And now here's where it's funny looking. It's always piecewise. And so it's the same kind of thing. So y can be in between A and B. And it's 0 otherwise. And then it just has a constant value in between A and B. 1 over B minus A. Right? And we'll check its conditions, but I'm going to do it in a very careless, a very embarrassing way called check by picture. So check conditions. You can look at the notes if you want to see some integral signs and stuff like. Sometimes that gives you a warm and fuzzy feeling to see integral signs, but And I get that, but sometimes they're cold. Check conditions by picture. All right, so what I'm going to do is I'm just going to plot that f that we've drawn there. All right, so that's y. And I don't know, let's say that a is here and b is there. And so what does the function look like? Well, it has a height. This height is 1 over b minus a, right? And then the function, if we draw it, okay, it's 0 everywhere here, right? So, okay, is it positive? Yeah. You can see it in the picture, right? Proof by picture. Yes, it's positive. Is it honest? Well, it's honest if the area underneath in that little rectangle, if this area is 1. And so what is this area here? It's the height times the width, or the width times height, whatever you want to say it. Right? So this is 1 over b minus a. That's the height. And then what's this width? That's b minus a. Right? So times b minus a. So that's 1. So it's honest and it's positive. And on that honest and positive note, we'll stop today's lecture.
So that's all for today. We've seen the whole family of discrete random variables that we're going to introduce in this class, and we've started to talk about continuous random variables and some of the little hitches that go along with trying to do that. Hope you had a good time, and I'll see you in the next lecture.